So powers of 10. We will come back and use powers of 10, but really our powers of 10 are just ways that we can scale numbers into a reasonable numbering system. Okay. I think we've talked about this. The human brain can really only comprehend numbers up to about 10. Right? Like that's why we invented the word a dozen. Okay. So when it comes to powers of 10, what we're doing is just trying to scale our numbers so that they make a little bit more sense to us. Okay. So we'll see powers of 10 with exponents, and ultimately where we end up shifting them to is things like scientific notation. So we could take a really large measurement or a really small measurement that has a bunch of placeholder zeros in it, and we could get rid of those placeholder zeros. That's what I get for eating lunch so fast. So that's the point of our scientific notation. I used to think scientific notation just meant you were using powers of 10. That's not officially true. Right? Your scientific notation has the requirement that you must have your first significant digit in the ones place, decimal point, all the other sig figs. Then your powers of 10. Okay, that is a requirement. So if we switched to, say, the top number, tried to write that out, we could go through and write 40.63 times 10. 1, 2, 3, 4, 5, 6, 7. We could say 40.63 times 10 to the 7th. Is that number the same as that number? Yes. Yeah. They hold the same meaning. Okay, I should also include the unit, meters. Okay, but what I wrote out is not scientific notation, which I thought was really kind of dumb when I discovered that. Okay, for it to be scientific notation, it must be written as 4.063 times 10 to the 8th meters. Okay, so just be kind of aware of that. It's a bit silly, but it's kind of nuanced within it. So how do we get to scientific notation? You can already see some of the stuff that I'm doing, showing the little curvy lines underneath. Depending on the use of your calculator, if it's been borrowed from the math department, you might see these little stupid curly cues written on the screen, okay, from people trying to count and convert scientific notation. I know mine at least was. Okay, so how do we go through and do it? Find your first significant digit, place a decimal point after it. So for the first one, it's 4. Second one, it's 1. Okay, do my decimal point in both cases, 4.063. For the bottom one, 1.16. Yeah? Yep. All right. Now we have to deal with the powers of 10. I definitely remember when I was a student hearing rules on how you figure out your powers of 10. If you go left, it's positive. You go right, it's negative, that kind of fun stuff. Ultimately, what I've discovered is that that is a load of crap, because depending on which direction you're going, scientific notation to the number, or the number to scientific notation, the direction you shift the decimal point changes, and you can now potentially screw up the meaning. Okay? So, let's kind of ignore what's written down there, I think. Yep. We take a look at what we've got written up here. For that 4 number, is that a big number or a small number? 406,300,000. Is that a big number? Yeah, it's a big number. Okay? That means my power of 10 is going to be positive. Okay? How positive is it going to be? Well, I've got my implied decimal point, and it shifted 1, 2, 3, 4, 5, 6, 7, 8 places, and I get 10 to the 8th. Okay? If we look at the number down below it, is that a really small number or a really big number? That is a very small number. So my power of 10 is going to be negative. Now when I go through 1, 2, 3, 4, 5, 6, 7, 10 to the negative 7. Okay? Both of these end up being meters, and we have our answers. So if we tried to convert the other direction, say looking at our power of 10, okay, we just need to make sure that we're shifting it, making it a small number, because it's a negative value. Kind of makes sense? So there's no more left and right. Okay? If that works for you and you're consistent and that's awesome, great, do it. Okay? But I don't know about you, I have problems with lefts and rights. So I could have quick issues with that. Make sense? Cool. Scientific notation. Scientific notation also has some added benefits that kind of tie back to sig figs. And this is kind of where other people have tried to say my sig fig rules have failed. And ultimately they haven't failed. It's just not looking at the data properly. Okay? Or ultimately not reporting the data. So if we take a look at that measurement, how many sig figs are there? 4, 6, 3, and the 0. So we get 4 sig figs. What about all those other zeros? Those are not significant digits because
they're not significant digits because you don't have a significant figure in between each other.
they don't have a significant digit to the left and to the right. And that's ultimately because we don't have a decimal point. Okay? So if we were to write that out in scientific notation, we could call that 4.063 times 10 to the, what do we say, 8 meters. We don't have to specify the positive. It's not bad to include it, but we don't have to specify it. Okay? So here's where this can get a little bit weird. Okay? And where the claim that I'm wrong with sig figs comes in. This measurement was taken, okay, but in the process of measuring it, they only measured to the thousands place. Thousands. How many sig figs in this measurement? Why are you changing your answer? Okay, so we say that again. The measurement is precise to the thousands. Jiminy. And I wrote it as a number because I thought I couldn't spell thousand. Screwed that up on both ends. Our thousands place. So why did you switch to 6?
Because the zeros are precise. It's like exactly what they are.
Those zeros are measured. If I'm measuring to the thousands place, those zeros actually have meaning. Those are significant digits. Why does that become a problem reporting the number as shown? Can I tell a difference between those purple significant digits and these blue insignificant digits? No. And if I dropped in a decimal point and put that there, well, now the purple ones become significant, but so do the blue ones. But the blue ones aren't significant, so I can't just put in a decimal point. So how can I report this number so that people know I measured to the thousands? That's where scientific notation comes in. Okay? So in the case of scientific notation, I would say it is 4.06300. Those are now all of my significant digits. There's all 6 sig figs. Times my power of 10, 10 to the still 8th power. I've now shown how I measured that distance using sig figs. None of the meaning changes, okay? But I've added some information into this. Red and purple now have different sig figs. I've changed the precision of the instrument being used. The red one was only precise to the 100,000s place, right? Yeah. And now I've switched it to thousands. Make sense? Yes.
So let me get this straight. So since the decimal was in the thousands place, you would have to go on the regular number to the thousands place, basically, and write that down, including that into the
Yes.
equation. All right.
Yeah. Those zeros are now significant.
All right.
Okay? So scientific notation allows me to be more precise in my language to ensure that people know what digits are significant and which digits aren't. Okay? Without scientific notation, I can't specify that information as cleanly. Okay? Short of going through and underlining and saying these are significant digits. Okay? And that gets a bit tedious. Kind of make sense?
Yeah.
Okay. So now we're into chapter 2, looking at our metric system. So your textbook calls these basic units, and I'm going to try my best to reference these as core units. Okay? And the textbook is technically wrong because the core or basic unit for mass is actually not a gram, it's actually a kilogram. Okay, so that one's a little bit weird. nuance, don't stress about it. When we look at length, our core unit is a meter. When we look at mass, it's a gram, volume, liters, time, seconds. Okay, time is a little bit weird. We could probably just delete that one off there because we get minutes and other things. Okay? This system, as far as the metric system goes, is pretty cool. Why would it be cooler than, say, the American system? Or what we use for our American system? Base 10. If we look at distances in the American system, we've got inches to feet. Well, how many inches are in 1 foot? 12. Okay? Well, but at least we're then consistent. We go from feet to yards, and there's 12 feet in a yard. No, it's 3 feet in a yard. Okay, well, then at least we're consistent when we go from yard to the next step up, miles. Well, then it's got to be 3 or 12, right? No, then it's something else. Okay, well, we created this system that had all sorts of weird kind of arbitrary numbers behind it. Some of that logic had to come from what was at hand. When I go through to measure distances, and I'm looking at measuring, say, 12 feet, that isn't that bad because what do you all have with you? Feet. So we could count out 12 feet and that wouldn't be a big deal. But if I try to count out 12 meters, how many of you are carrying around a meter stick? Okay. So depending on the system we're working in, we'd have different kind of measurement systems and what would be at hand. So to a certain extent, that Greek system, feet and inches, or the American system as we're using it, is kind of useful because we always have those measuring tools available to us within a ballpark approximation. Right? When we shift to the metric system, we now actually need a measuring device, okay, a meter stick, okay, a balance that measures grams. Okay, so we'd have to create a new system to go through and measure those. That system now invented, it goes by powers of 10, which is kind of cool because we literally just talked about powers of 10. It's amazing. It's like someone planned these things. Okay? So we can take the powers of 10 to scaffold into higher or smaller units and just change the power of 10 to give a different meaning. Okay? So we can say a millimeter, and all we have to do is recognize that if I say a millimeter, I'm looking at the core unit of meters, but I'm operating on it with the milli meaning. What does a milli mean? It's on the board. 10 to the negative 3. So if I have memorized what these prefixes mean, back to these powers of 10, I can scaffold really high units and I can scaffold really low units very quickly without having to deal with, well, it's times 12, it's times 3, it's times 5,280. Okay? We have a system that is easily scalable, and that's kind of a big benefit. That does mean we have to be able to interconvert between them, and that does mean that we have to memorize the meaning of these prefixes back to their powers of 10. Okay? It is my recommendation, though not a requirement, that you memorize the one-letter code to the power of 10 listed next to it. For those who think, well, that seems pretty straightforward, we'll encounter some cases where you've probably gone through and memorized something else. Okay? But tying the prefix to that power of 10 is going to become super important for being able to easily and quickly and correctly, consistently convert these different unit systems. Okay? So of those, how many do you think we'll actually use? Are we going to measure a teragram of something? Okay, probably not. Okay, and since it's not a computer class, we don't have to worry about terabytes. Okay? Wasn't really supposed to be a joke. Kind of sounded like a delivery of one, but so how many of these should we bother to memorize? 4. Seems like kind of a random number. Why 4? Which 4 do you want to memorize? Kilo is a good one to memorize. Centi is a good one to memorize, I agree. Milli, that's a good one to memorize. Deci's not a bad idea, so we could try and box in deci. Survey says 3. I'll need you to memorize 3. Kilo, centi, milli. This does not mean you won't be expected to use the other ones. Okay? But on an exam, I would give you that context. Okay? In the homework, you're expected to look these up so that you can use them. Okay? But kilo, centi, milli should be committed to memory. Why? Because I tell you to, and that's not bad. There was another suggestion over here. These are the most common ones that you see. Because they show up commonly, that's why you should memorize them. This is why you all memorized what the symbol for C was. Carbon, but you didn't bother to memorize what the symbol for CE was.
Oh, wait. There is no.
Okay, there is CE, 58. Okay. You're not commonly using it. So when you went through to memorize the elements, what you should have been memorizing were the more commonly used ones. So when I tell you to memorize things, it's not because I'm arbitrarily coming up with these. It's because they get used fairly frequently. If you memorize them, you shorten the amount of work you have to do. Okay? So you should go through and memorize those 3. They memorized. Good. Use them. Okay? I want you to convert the number into scientific notation and tell me what the new unit is. Scientific notation use powers of 10. Our new units use powers of 10. So let's take a look at what I mean. Start with the first one. Scientific notation. This would be 1.2. Those zeros are now acting as placeholders. Times 10. I shifted the decimal 3 places. That number is larger than 1, so it's a positive value. And I get meters. Yeah? 1.2 times 10 to the 3rd meters. What is my new unit? Well, it's going to be 1.2 10 to the 3rd meant kilo, so I have kilo meters. There's my new unit. Your turn. 3 more. If you got questions, raise your hand. And someone pointed out, they're like, why would you put them all as 1.2? Because I'm not creative. Thank you for calling attention to that. 1.2, we look, how far did we shift that decimal? 2 places, which means this needs to be 10, 2. But because this is a number that is less than 1, that needs to be a negative. Okay? What did 10 to the negative 2 mean? What did it mean? Centi. So this becomes centi seconds. 1.2 centiseconds. That easy. It's kind of cool. It's like someone planned the into part of, yes, they planned it. The next one. How far did we shift the decimal? 2 places again. Again, negative. And this becomes centiliter. Last one. We shifted 3 places. So negative 3, and we get milligrams. Okay? It's a lovely system that allows us to deal with that conversion, and we can swiftly kind of deal with scaling up or down from these. Okay? There are other approaches to doing these conversions, and we'll see those when we deal with conversions. Probably not today. Maybe, I can't remember. We'll see. Okay, questions about that? Okay. So, this is important to get those memorized. So, make sure you've got it memorized. The next thing I kind of want to deal with is this fractional notation aspect, because this is kind of how we would look at another conversion. If we look at it in English, there are 1,000 meters in 1 kilometer. Yes? Okay. In mathematics, 1 kilometer equals 1 km, which equals 1,000 m, right? We've made some simplifications. Can we, play around with the mathematics a little bit? Yeah, why not? Because I don't like math. Sorry. Got to do it anyway. Okay? I'm going to say do this. So I'm going to divide that side by 1 kilometer. If I do that, what else do I have to do? I'll do it the same on the other side. What is 1 kilometer divided by 1 kilometer? 1. What is this now? A ratio, and in particular, this is a ratio that we can use to convert meters and kilometers. So if, for instance, I say gave you, that's a horrible looking 3, let's try that again, 3.2 kilometers, and I wanted you to convert that into meters. Okay, so one option, and I think I heard what you were saying, well, couldn't you just move the decimal? Yes. Which way do you move the decimal? Depends on which number I'm converting. That depends requires a little bit more cognitive thought, which then means some of the time you screw it up. Okay? 60% of the time you're right, that's fantastic. How many of you are going to be happy with a 60% grade? Okay, so that means just shifting the decimal was a stupid idea of your math teachers to tell you to do. Okay? You could scale it up to 70%, 80%. 80%, you might be like, I'm trying to be happy with that. Okay? I would argue any real failure there that's larger than 5% was a bad idea. Okay? I want 95% confidence levels. Right? So, what can I do? Does the unit of kilometers need to show up in my answer? There's my answer. Do I see kilometers? No. So it's here, which means kilometers needs to show up in the denominator. What needs to show up in the numerator? Meters. Hey, look at that. I just rearranged one. There it is. Now all I got to do, put it together, and mathematically, there we go. We've got it. What did I just do? What is this value equal to in purple? What is that value? 1. All a conversion is multiplying by 1. That's why they work. If you don't multiply by 1, it's not a conversion, and you screwed up pretty royally. The problem lies with what is the 1 that you decide to multiply by. What do I mean by that? In purple, what is the value in that purple box?
1.
It is also 1. But that doesn't say 1, right? What could I do? Where did that 1 come from? Coming from the equality. It's just a question of which one do I want to use. Do I want to use the one with kilometers on top or kilometers in the numerator? Sorry, that's the same thing. In the denominator. Okay? I have to make that conscious effort and that conscious decision behind the conversion. Those are going, well, damn, that shifting by a decimal point starting to sound better and better. This is just the intro in. Largely what we're talking about at this point is setting you up with a process that works all of the time. You have a process that works 80% of the time. You can trust and rely on that process, and you can check my process. What I want you to do in this unit is to prove to yourself that my process works. And it's not mine, by the way, just for the record. I didn't own it. Okay? But that's what I want you to do. I want you to prove that this works so that when we move to a different system where you have no idea the concept of the numbers or the units, you can trust my process and you can get the right answer. That's the point of this unit. This unit is not about I can deal with meters to kilometers because everybody can do that. In fact, your calculator can do that in most cases. Okay? What we need to do is come up with a process that allows us to deal with things outside of those unit systems. This is the process we're working with. All we're doing is multiplying by 1. We have to make sure we know which one we want to look at. Should I throw in another example on this? I heard a no, we're good. I'm going to do it anyway because I think it's silly. That's the appropriate response. Okay, Mike, do whatever you want. 12 inches is 1 foot, correct? Is the purple box 1? Yeah. Is that a useful conversion? No. Okay. The whole process is figuring out what conversion you should put in there. Okay, so you will have to pull from and find those conversions in a variety of different sources through the course of this class. In this first unit or second unit that we're dealing with, those conversions are largely provided for you. You just have to deal with it. After that, they're provided for you as well, but they're buried somewhere. Where would they be buried? In the periodic table. We have a bunch of conversion factors already built in there. You now will have to start to learn how to pull that information out so that you can use it. Okay? So that you don't have to, say, memorize there's 12 inches in 1 foot. Okay? That information is already there as long as you know how to manipulate it. Okay? So English, mathematics, and then useful mathematics, looking at the fractions. Okay? There's a bunch of other stuff there. We'll just skip over that. This one almost always seems to kind of boggle people's minds a little bit, so let's approach this a little bit carefully. What does the negative or positive mean? It's actually a really challenging concept, and believe it or not, it tends to break most students when dealing with anything numeric. The positive really doesn't mean anything. We just do it. If I'm going to walk in the positive direction, I just walk forwards, right? What happens when I walk in the negative direction? So I turn around and now I'm walking backwards?
No, like you step.
Oh no, literally I just have to step backwards. Okay? So the negative just means go the opposite direction of where you currently are. Don't do any spinning or rotating, just do the opposite thing. 10 to the positive 2, just run it. 10 to the positive 2 means I'm going to run that calculation where it is located. Where is it located? Like, that's a hard question. Let's make it easier. Where's that calculation located?
One's place.
I'm not trying to be a complete jerk on this, just making sure we're all catching up. Stop laughing, that's legit. Where's the calculation located? The numerator or top. So our answer becomes 100. How about here? We actually color code. Says run the calculation in the opposite location of where it is. Where is it located? In the numerator, which means run this calculation in the denominator.
So it just
Seriously? Like, that's it? Yeah. That's what the minus sign means. Okay, it means do the opposite of what you think you're doing. Just do the opposite. And you're like, well, that's not that big a deal. I add an electron. What's the charge? Yeah, that long pause. I subtract an electron. Okay? That negative sign is a challenging thing to deal with. And the negative sign will haunt you through chemistry. Okay? It has a mathematical symbol associated with it, and we can just punch it into the calculator and deal with it. As long as you don't lose the minus sign, you're okay. You can also track the meaning to get the same effort. Okay? So, why mention this? Centimeters and meters. Right? Centi is 10 to the minus 2. So 1 centimeter, 10 to the minus 2 meters, right? Everybody agree with that? Cool. So quick question. How many centimeters are in a meter? I heard 100. You memorized something, didn't you? You memorized 100. 10 to the what? What is 100? 10 to the second. Is that what I told you to memorize over here? Doesn't that say 10 to the minus 2? Why did you memorize 100?
Because 10 to the 2 was 100, and it was a whole number, and then the opposite of that would have been a fraction.
10 to the minus 2 ends up dealing with fractions and negatives. The human brain does not do well with fractions and negatives. Okay? Because we did not have technology appropriate enough to deal with fractions and negatives, we converted that number through this mathematical manipulation into something that we could better comprehend. 10 to the minus 2 means run the calculation in the opposite location of where it is. Where's the 10 to the 2 currently located? Denominator. So if I'm going to run it in the opposite location, I need to place it in the numerator. What happens? What did you memorize? There it is. So that thing that you memorized on 100 centimeters in 1 meter, that's fantastic. That's awesome. You probably also did it for millimeters. You've probably also done it for kilometers. Interestingly enough, those are the 3 things I told you to go through and memorize. The reason why I'm addressing this is that if you've memorized it by this whole number power of 10 stuff, you will likely screw up your conversions. Okay? And the time that you're going to screw it up is on the exam. Okay? When I tell you to memorize what a centi means, it's 10 to the minus 2. And you might be like, well, I don't like dealing with fractions or powers of 10, okay, or negative numbers. Okay? The people that came up with it and said 100 centimeters is 1 meter agreed with you. But they were missing something that you have. What were they missing?
Calculator.
A calculator. I was going to say an awesome teacher, but thank you for not laughing at that. That's appropriate. Okay? A calculator. Do you have a calculator?
Yes.
Does it do powers of 10? Does it do negative powers of 10?
Yes.
Use it.
Okay.
Okay? There is no need to memorize a bunch of useless information when you have a calculator that'll do it for you. Okay? You'll never have a calculator the rest of your life. And yeah, you pull out a calculator and you're like, hey, look at my phone. Look at this, calculator, duh. You've got one. You can always have one. You don't need to memorize this extra useless information. Dealing with the centi, milli, and kilo based off of that power of 10 flow chart will always work, and it will always be consistent with how you solve. Shifting into the powers of 10 with these whole number things, the problem with that is you have a tendency to misuse it. Okay? I promise you, you will misuse it. Okay? So if you ever hear someone say, well, which is bigger, a kilometer or a meter? You're like, I don't care. Calculator. Okay? That's what we're getting at. That question of being able to convert between meters and kilometers or millimeters and meters. Okay? Where someone says, well, which one's bigger or which one's smaller? If you freaking knew the answer to that, you wouldn't have gotten it wrong. Okay? So that question is an annoying question. Admittedly, I've heard lots of tutors ask that question of students. And I usually freak out a little bit. But let's go a little personal. I've asked that question of students. It's a stupid question to ask. If people knew that conversion, they wouldn't have an issue with the conversion. Okay? So if someone asks you that, just be like, well, hold up. I honestly, I don't know that. You can't use that as an example to help me. Okay? Make sense? Ish? Ish is good enough. So, deep breath. Mike can stop yelling at me now. Okay. So, qualitative and quantitative, we'll jump back into chapter 3 for a little bit. Chemical and physical properties. Okay. Your physical properties are observable characteristics that don't change the elemental composition. Okay, so we don't make or break chemical bonds. Now that we have a rough idea of Lewis structure, we know what chemical bonds are. We don't make or break those. Okay, the hard part is, well, how do I know if I've made or broken those? Okay, that's the challenge that you probably encountered when you did that lab, physical and chemical changes. Okay? Chemical properties talk about the properties that happen as we make or break bonds. Okay, so it's all looking at the bonds. Because we don't see bonds, this becomes challenging. Okay? The biggest thing that we're going to look at is primarily with the change. So physical changes, you can change and alter what's happening or the phase that it's in, but you can't change the bonds. Chemical change, you're changing the bonds. So how do we know which one's which? Well, conveniently, we have a list of all the things that signify chemical changes, right? Okay? And because we all watch the play pause on it, you'll be able to tell me change in phase is an example of a chemical reaction. Okay? If I take ice and put it in my hand, what's happening to the ice? It melts and becomes? Water. Liquid water, right? We went from a solid to a liquid. Did I change phase? Yes. Nick, what did you say a change in phase was?
Chemical reaction.
So melting ice is a chemical reaction? No, it's not. It's a physical change. We didn't break any chemical bonds. But didn't we just say a change in phase is a chemical reaction? But you're not changing the chemical components. How do you know that?
Because frozen H2O is the same as liquid H2O.
How do you know that?
This is read it as not heat induced.
Okay, so one option is to look at what's causing that change. Okay, the big tip off here is that it's not heat induced. I haven't added heat or removed heat. Well, I'm not adding heat by taking the ice and putting it in my hand, am I?
Yeah.
I'm taking heat out of my hand. Okay, I'm just going to put it on the desk. I'm still taking heat out of the air. Okay, so I am providing that heat in both of those cases. And that's where it can become challenging, is dealing with that heat, with that phase change. Okay, so let's take two liquids. I mix these two liquids and I see a gas. When do I see a liquid transition to a gas? When I heat it. I've taken two liquids and I've mixed them. Have I added heat? No. What's causing the gas? Okay. Chemicals are providing the energy to cause the liquid to go into the gas. The phase transition is caused by the chemicals supplying the energy, not me. Okay? So when we're looking at our chemical reactions or the evidence of chemical reactions, what we're trying to decide is what's causing or what's providing the energy to allow for that change to occur. Phase changes are awesome examples of it, going into the gas or forming solids. Okay, your textbook has those listed as two different things. It's a change in phase. Okay? So if you see a solid formed, it's most commonly referred to as formation of a precipitate. That's a red flag for a chemical reaction, assuming I didn't say put the liquid in the freezer, because now I'm supplying or removing the energy from it by putting it in the freezer. Okay? If the chemicals are mixed and a solid forms on their own, they've dealt with the energy, not me. Kind of, sort of? Permanent color change, chemical or physical? Okay. Has anybody taken red food dye? White cake frosting? And you mix them? What color does the white cake frosting come? Pink. Chemical or physical? You can't reverse that. Not true. Turns out you absolutely can reverse that. You have to be very careful in your process behind it, but what you can do is add a drop of food coloring into it, and as long as you move in the exact same circle and reverse the exact same direction, you can absolutely reverse that. There's actually a video that shows it. It's pretty fascinating. Okay?
But like once it's in there, you can't just like.
Well, you physically put them together, so yeah. So a permanent color change, you can't reverse. So we get this concept of reversibility being tied to these. Okay? Reversibility is still a little bit borderline because you can pretty much reverse everything. Okay? Had a horrible fight and you're never going to get back together with your significant other. 5 weeks later, hey, you're back together. What happened? Bought me a cool toy. I decided it was worth it. Okay? There's always a cost to it, but there is some aspect of that reversibility that gets a little bit dangerous to use. The other big one is an energy change. Okay, the release of heat. If I mix two liquids, why is it getting hot? Okay? Because the chemicals are releasing that heat. That's why the solution's getting hot. Okay, it's not I put a pot of water on the stove, turned on the stove, and was like, oh my God, the water's hot. Must be a chemical reaction. No, you added the heat to it. Okay? That's caused by you, not the chemicals. Okay? So when we think about these chemical versus physical changes, we have to be a little bit careful to kind of nuance the details between chemical and physical. And even then, there's lots of gray area, as I believe was addressed. Oh, it actually wasn't addressed by the video. So we got pictures, we got bubbles, formation of a gas. We've got a color change and a phase change. This is a solid. That's why we can't see through it anymore. Okay? And what's going on with that last one? Sparks. What are sparks? Energy. Light is a form of energy. So we're seeing energy released. Okay? So, here we go. Chemical or physical? It's a nice little fun one. Melting ice. I completely agree. That is physical. Dissolving sugar. That's interesting. There's a little bit of a mixture there. Turns out dissolving sugar is physical. Burning wood. That is absolutely chemical. Mixing red food dye. Well, yeah, that's kind of boring. We already did that, right? We said that was chemical, right?
Mm-hmm.
No, we didn't. We said that was physical.
Keeping you on your toes.
Yeah, okay, fair enough. Fair trade. Okay, now we got two interesting examples. I'm going to skip salt for the moment and look at this last one because I find this personally kind of cool. We're starting with yellow crystals. We shine light on them and what happens? They change color. We remove the light, what happens? They go back. Chemical or physical?
Physical.
Why are you saying physical? Because it's reversible. Turns out, guess what? It's actually chemical. We are changing the chemical bonds within that structure. Those bonds happen to be easily broken and reformed so that the reversibility happens pretty quickly. So we actually get a chemical process. For those people going, wow, that's kind of crazy, I've never seen that before, it's because you aren't old enough. Back in like the 80s, they had the color-changing shirts. You're like, what? Yeah, they had color-changing shirts. Okay, that's way back there. So for more currently, there's not a lot of people wearing glasses in here, but they have fancy glasses where when you walk outside, they change to being dark. It's the exact same process. They've embedded that compound inside the glasses so they change colors.
How about mood rings? Did you notice the
I'm pretty sure mood rings are a thermal... Actually, I'm not sure exactly how mood rings work, but I don't think it's this process. Okay? I know it's thermal, yeah. I just don't know what chemically it's doing.
Is that chemical change or physical change?
So, and there's a good question. How do we know chemical or physical? And you notice that I'm deflecting that question very quickly because I have no idea. Because I don't know what's actually happening in that substance. You have to have a larger context of what that substance is to cause the change, which is going to get to the next big question. Because most of you have not had me for lab, hopefully you'll all screw it up.
Thank you.
You're welcome. Dissolving salt.
Chemical.
It's the random green color.
You can undo it. Okay? Dissolving sugar, you could undo, right? It's reversible. Down here, we could reverse. Anybody notice anything interesting about the stars I've been dropping in here? They're different color. They also kind of correspond to the color line being shown across the top. Chemical and physical is not a black and white system, it's a spectrum. Okay? Depending on where we're falling with that process on that spectrum, we may be able to clearly define it as chemical, burning wood, or melting ice, physical.
Well, that's why you did the color
Okay.
stars the way they are.
The dissolving sugar typically gets classed hardcore physical. We had a few people balking on that, so I made it orange. But that is typically referenced as physical. Why? When I dissolve that white substance in water, nothing happens to the chemical bonds in sugar. Salt also happens to be a white substance that looks exactly the same as the sugar in water. And yet, when I dissolve salt in water, what happens? I break the ionic bonds in the salt molecule, meaning dissolving salt is chemical. The exact same physical observations, and yet we're ending with a different result. And that's because dissolving salt sits right on that borderline between chemical and physical. Our observations don't allow us to differentiate that very well. And that is challenging. And that's what I want you to recognize with chemical and physical. It requires a broader context to understand exactly what is happening. How could we prove that dissolving salt actually broke the bonds? Well, we could try and run a chemical reaction. If those ions on their own were present, we could prove that a reaction happened. Say like taking table salt, adding it to water, and then, I don't know, adding some AgNO3, also known as silver nitrate, which in that case resulted in a white cloudy substance. And when I did that exact same experiment with the sugar, what happened? If I actually did it correctly. Nothing. Silver nitrate is reacting with chloride ions. That's why I see the white cloudy substance. I don't see any special substances with the sugar because I didn't break any bonds. I know the bond is broken with the silver nitrate because I see an end result of it having happened. Okay? And those of you saying, well, but we didn't have that test, go back and take a look at your physical and chemical changes lab. You did. Okay? Just because you did it doesn't mean you knew what you did. That's fine. Okay? But that's actually why it was designed that way, is to allow you to help see what's happening and to make sure you could identify that dissolving salt actually is a chemical process. Okay? So, when it comes to chemical and physical, what will you get tested on? How many of you feel like I should test the green area? No? Okay, what do you think I'm going to test on? Red versus purple. We'll pick the big extremes, and even then, those get dicey because we're looking at your external experiences. Okay? So, states of matter and equations, because this was in the video, you guys should have been able to figure all these out. Do you guys have any questions about what's up there? Okay. We'll just kind of throw this out there. Does anybody want to volunteer and be like, I totally did not watch the video? Okay, just curious. So the rest of you all watched the video or didn't volunteer, right?
You're going to make us do something if we say we did watch the video. So should I raise my hand and say I didn't?
I have no idea what you mean.
I watched it, but I forgot everything. So.
No, I'm not going to do anything like that. Really, all I wanted to know was that if I skip over this, we're okay. Like, you understand the basics behind this? So people that watched understand what the pieces are, so that the people that didn't watch will be like, I still don't know, but you can watch the video and figure it out. Yeah. Okay. So when we look at a chemical change, there's some little laws that pop up. You get this guy coming in with Proust saying you get the law of definite composition. Okay. All this is saying is that our compounds contain the same elements in a constant proportion by mass. That's it. That was easy. What we're saying is that when we look at water, what's in water? Is that all this is saying? This is saying a constant proportion. So when I look at water, is it just hydrogen and oxygen? Because if I just wrote hydrogen and oxygen, would you say that's water? No, it's 2 hydrogens and 1 oxygen. Okay? But that's the amount of the atom. Proust is actually before atoms. He's measuring this based off of mass. So he's saying that when we look at water, water's always going to have 2 grams of hydrogen and 16 grams of oxygen. How did I come up with those numbers? What do you mean the periodic table? What is the mass of hydrogen?
It says 1, but you're having 2.
1, because there's 2 hydrogens, there's 2, and oxygen,
16.
16. We got mass on our periodic table. Okay, yes, the grams is a little bit weird. Don't stress about that. Okay? But we've got mass. The periodic table shows this information. We had access to the mass, so we could see that we had these constant proportions. This is one of the things that Dalton uses to refine and come up with his atomic theory. Okay? How can we measure these things? I thought that was kind of weird that even before Dalton, they were able to determine the mass of elements in each compound. I mean, that seems kind of bizarre. Okay? There are ways you can go through and do it. You will actually do some of these experiments in lab. Okay? If we heat up potassium perchlorate, okay, it'll decompose into potassium chloride and oxygen. Okay? So we could determine the exact masses of each of those compounds. So we could take varying amounts of potassium perchlorate and we could just heat it up and see what happens with those mass ratios. And we would notice the mass ratios were always the same. So there are ways to go through and observe this. They're a little bit tricky, but we can do it. Okay? That's where we get Dalton coming in, coming up with our atomic theory, which we then explode and do all sorts of nuclear stuff and all that fun stuff that we already talked about. Yeah? Cool. So what do we do with that? Well, we now have atoms. We now know that we can combine atoms to make different things. We could go through and look at a chemical equation that would represent that process. So this equation we already walked through. Okay? We now have a chemical reaction that describes how this process happens. I take sodium hydride with acetic acid, and when I mix them together, they form sodium acetate and hydrogen gas. Okay? That's what that chemical equation means. Okay? The next part that comes useful behind this is that we have to acknowledge that that recipe has to be correctly balanced. We have to have the proper ratios. Okay? For instance, if I'm going to make jalapeno poppers, I need jalapenos and I need cheese. Okay? So if I go to Costco and I buy that big old block of Tillamook cheese and I buy 5 jalapenos, why are you saying those are going to be some good peppers? They're going to be stuffed full of cheese. Okay? The amounts are kind of important to match those things up, right? Costco's a 5-pound block of cheese. That's a big cheese. Okay? 5 peppers, like your finger's a pepper, roughly. 5. Okay? That's not going to work right. Okay? So the ratio behind those is important. Okay? Baking. I need flour and sugar and let's go with flour and butter to make a crust. Okay, so I'm going to take a tablespoon of flour and 5 pounds of butter. No, that doesn't quite work. Those ratios are important. Our chemical equation incorporates a lot of that information in it. Okay, but the way it's incorporated is based off of the number of atoms present, not based off of the mass. So when I look at this chemical equation, I need to go through and decide, is it balanced? Does it have the same amount of each of those things at the beginning and the end? Because if it doesn't, I can't pull information out of the chemical equation. Okay? The video you watched broke down a process behind it, which you can now guide me through.
So on the left, you're saying you have, like, let's just say, for instance, like 1 egg and 5 tablespoons of whatever. And then adding those together is what's on the right.
Yes.
Okay.
Okay. So I take one egg, bunch of cheese, and I put them together, and I end up with a quiche. It's not that far off. Okay. Not, I take my, how many eggs did I say? One egg?
One egg.
One egg. I didn't count right. It's a small quiche. It's for ants. Okay. I take a single egg, a little bit of cheese, and I end up with a quiche and like a pie.
What?
My pies have eggs in them. I don't know. Okay. I don't have those extra components. Where did the flour come from to make the pie? Where did the strawberries come from? You just said eggs and sugar, and all of a sudden you got a strawberry pie? How'd you do that? Okay, yeah, you're like, what? That makes no sense. Chemical equations need to make sense. Okay, so we need to make sure that the components show up on both sides. So, walk me through it.
Well, first off, you want to make sure the sodiums are balanced. So you put in a.
So, what we'll do is break it apart into the pieces. We could say a sodium hydride show up the same on both sides. If we did that, that would be like looking at my pie and saying all the eggshells went into the... I keep saying pies. My quiche. And I put all the eggshells in the quiche. I don't want to do that. It's going to ruin my quiche. So I'm going to break it apart. Sodium, how many sodiums do I have on the left?
One.
On the right?
One.
Now what do I want to do? Okay. So we've got a suggestion for hydrogen. I'm going to argue that hydrogen is actually a bad idea to work with. Why would hydrogen be a challenging element to balance? It shows up in every single place. So if I have to try and balance, which one do I change? If I change one, it's going to mess with everything else. So I would not touch hydrogen first because it shows up in too many different places. So what do I want to balance then? Carbon. How many carbons do I have on the left?
2.
On the right?
2.
Now what? Oxygen. How many oxygens on the left?
2.
And
2.
2. Hydrogens?
5. This is honorary.
Yep, I agree. Yep, I agree. Which then means it's balanced. So this was a pretty awesome chorus of yeses. You totally understood what was going on. So I think that's pretty fantastic. So what we'll do, since you already know all the rules, we can just skip over the rules and we can just jump straight to practice for you all. And if I did that right, I deleted the one that I walked through in the video.
You did?
Yeah.
Look at that.
Wow.
Now you guys get to go through and balance those. A couple things kind of popped up as we go through and solve these. So personal preference behind these. Let's start with that first one that we can see, the hydrogen and the bromine. Okay, you'll notice that what I will do is list the hydrogen underneath. This case, it's okay to start with hydrogen because it only shows up in one place on both sides of the equation, so it doesn't really matter. Okay? How many hydrogens on the left? 2. How many hydrogens on the right? 1. So what do I need to do? I put a 2 in front. That now makes that a 2. Okay? And here's where I'm going to take a step back and we're going to kind of rewind. Because I'll get people saying buts and other things like that. Okay? So if there's a 1, they go, okay, well, bromine, there was 2 and there's 1. And I say, whoa, stop. Okay? By doing that, you are now actually going through and totaling everything up each and every single time you have to check this. Okay? It's not necessarily a bad thing, but if you have to cycle through and check multiple times, you're going to lose track of what element you're working with, and you can potentially make mistakes. As soon as you find out you are not balanced, fix the issue right out of the gate. I don't care about bromine right now, I care about hydrogen, and it's not balanced. So I'm going to make that 2 so that it is balanced. Okay? Fix it immediately. Now when I move to the bromine, how many bromines on the left?
2.
I don't know why I did that. Sorry. 2. How many bromines on the right?
2.
2. There's no but. It's balanced. Okay? So I don't have to then go, well, now which one do I have to balance? It's in sequence. Okay? If you look back at the rules, we're not done. What do the rules say to do? How many hydrogens on the left?
2,
Hydrogens on the right.
2,
How many bromines on the left?
2,
On the right?
2.
What do the rules say to do now?
Place one in front.
How many hydrogens on the left? On the right? Bromines on the left? And what do the directions say to do now?
Place one.
How many hydrogens on the right? How many hydrogens on the right? Hydrogens on the left?
2.
Bromines on the left? And?
Repeat 3 and 4 until after.
What was that?
What? Oh, repeat 3 and 4 with new.
You need to repeat your process through multiple times. Okay? This is one of those cases where I would say that you should repeat this. And some people, not to name names, aren't confident in the balancing process and might say, well, they don't want people looking at their work. This is one case where you should be dead confident that you are 100% right. Because if you're right, what happens when you check it?
It's going to be nice.
It's going to be balanced. It's going to check. You know you're right. Or you know you don't. There isn't a middle ground. It either balanced or it didn't. Okay? And if it didn't, you know you got it wrong. Okay? Check the work. Okay? My general recommendation is you should check it so many times that you're like, why the hell is Mike making me check this so many freaking times? Because that brings in just a little bit of kind of angst, a little bit of anger, builds a little emotion. It's going to lock it in your brain, and you're going to remember it, and you're not going to screw it up on the test. Okay? If you just go, yeah, whatever, I don't really trust Mike anyway, you're going to forget. Okay? So just get a little irritated at me. Not so irritated that you're like, screw this, I'm going to fail this class just to spite Mike. Okay? But just enough to be like, I'm going to remember this so that I never see Mike again. Okay? Kinda? Next one. How do we approach it?
Do aluminum first.
How many aluminums on the left? 2. On the right? 1. What do I do?
Put 2 on the
Immediately fix the aluminum. The suggestion, Becky, is
2 on the aluminum.
I put a 2 in front of the aluminum here. I don't change the subscript, because if I change the subscript, I'm changing the compound. I'm changing the formula. I'm not allowed to do that when balancing. Okay? Now what do I do? Okay, I heard barium, so barium. And there are 2.
Oh, 2.
Why are you shaking your head?
This belongs
The barium goes to the parentheses. And only the parentheses, that 2. Okay? Not the barium. So there's only 1. How many bariums on the right? 1. Is the barium balanced? Yeah, now what do we do? You get kind of a couple options here. I will see students going through and doing sulfur. Okay? Then nitrogen and then oxygen. That is fine. Okay, but we have a cheat. What is SO for? Sulfate. What is SO for? Sulfate, which means it's the same. That is now its own element. I can balance it as an element. As long as its formula does not change, I can balance it just like I can balance any other element. How many sulfates on the left? 3. We now do have to watch out for that parentheses. On the right? 1. How do I make it a 3?
You gotta multiply by 3.
Put the 3 in front. Nitrates. Okay, I heard someone say something, but then the barium. I don't care about the barium. I already did the barium. Nitrate. How many nitrates?
2.
Nitrates. Try again. Why 6? The 3 goes to the parentheses, the 2 goes backwards. There's 6.
Oh, okay.
Okay, how do I fix it?
Put 3 over there.
Oh, no.
Okay. Now what do I do?
Now you gotta go rinse it back in.
Six. And do it again.
Do it again.
Rinse and repeat. Barium.
Oh,
Wait,
three.
3 and 3. I'll get to that, I promise. Aluminum.
2 and 2.
2 and 2. What's next? I'm looking at nitrate, so we're going to do nitrate.
6 and 6.
6 and 6. Sulfate.
3 and 3.
Did it balance?
Yeah.
Yep.
What do we do?
Check it again.
You check it again. Okay? I would argue if you really want to cut down on the checking, which makes sense. Anytime you change a number, you check it. If you cycle through and you didn't change a number, you're either right or you were way wrong. Okay? You probably don't need to check it again if you don't change a number. Okay? If we go back to the barium, I didn't worry about it, and look what happened. It fixed itself. Okay? Start in a linear fashion and just cycle through. The cycling through can just simplify and check things as you go through it. So use that to your advantage.
And so the quotation marks around, the parentheses around each of those elements, each of those compounds, with the number 3 on the right just indicates how many there is of them, right?
Yes. So the parentheses are providing the context to make sure you know where that 3 is referencing.
All right, that makes sense.
Okay?
That's what I was questioning.
So with that, we'll go ahead and finish. I will be going to office hours if you got